So I actually wanted to begin by just contrasting the way I presented it with the way Hawking did so originally. So remember, in our derivation, okay, I've tried to sketch the Penrose diagram for the collapsing star. The star is this shaded bit. Then there were two important surfaces here. The surface S prime, where the observer lives, and the surface S was a convenient choice. Actually, I didn't draw it quite well enough. It's convenient because it crosses the horizon outside of the star. I didn't quite draw that properly. And it's supposed to cross the horizon enough after the collapsing star so that along S, things have settled down. Now, Hawking didn't introduce originally the surface S. He did, of course, have the observer somewhere up on S prime. And then what he did was to, in the same way I explained in the end of the lecture, he integrated backwards in time to evaluate the observer's measurement in terms of something. But since he didn't have the surface S, he went all the way back to the past infinity. So in Hawking's presentation, what you measure on S prime, you'd integrate back inside the star and all the way back to past infinity, where the energy was exponentially large. And then, roughly, he argued that since the energy was exponentially large, the wave propagates freely in through the star and then back out again, and then eventually meets that potential barrier, which he had to analyze roughly as we did. This kind of raises extraneous questions because we don't know what a wave of exponentially large energy would do when it propagates through a star. And Hawking was ignoring all that. So an improvement, which as far as I know was first made by Friedenhagen, was built into my lecture today and also yesterday, was to trace the signal back not to the far past as Hawking did originally, but just to someplace outside the collapsing star. And then one of the reasons that's important is that we never have to talk about energies where we don't know the laws of nature. So for fun, I always kid you about exponentially large energies where the signal arises, but that only means exponentially large compared to the Hawking temperature. So for example, if we have an astrophysical black hole where the size of the black hole is maybe 10 kilometers, so the wavelength of the outgoing Hawking quanta are also of order 10 kilometers. An example of a very short wavelength would be a millimeter. So we could place the surface S such that the outgoing wave we're planning to observe had a wavelength of a millimeter there, small enough compared to the size of the star that it can be regarded as an extremely small wavelength, but large enough so that we're in no doubt about our knowledge of the laws of nature there. So in this version of the derivation, we only use the laws of nature where we know them. In Hawking's original version, it raises extraneous issues because it appears to involve the laws of nature where we don't know them, where this exponentially high frequency wave is propagating through the star, going in and then back out. So that's one difference from Hawking's derivation. The other difference in my presentation from Hawking's is that on the first go I cheated, ignoring the potential barrier outside the star and imagining that the wave just propagates freely to infinity. So we only had to make a simple change of coordinates. So Hawking's original paper didn't cheat in that way. So these are basically the two differences between what I explained and what you'd find in Hawking's original paper. Any questions on that? Okay. So I realized as soon as the lecture was over that it wasn't true that I'd finished section 4 because there was another topic I wanted to discuss, which is the following. So in our presentation, the possibility of thermal equilibrium between the black hole and radiation was important because we used it to intuitively motivate the answer that we then derived, which is that the role of the potential barrier was to suppress the outgoing radiation by this factor of transmission amplitude squared, or transmission probability. But since we did make use of the notion of thermal equilibrium between the black hole and radiation, I thought I should explain that that notion actually is a little bit problematical because the thermal ensemble, so thermal equilibrium of the black hole plus radiation with zero cosmological constant is actually unstable. So the instabilities can be cured, as we'll eventually explain, by taking a non-zero cosmological constant. But with zero cosmological constant, there actually are two instabilities. Roughly speaking, one instability involves the black hole and the other involves the radiation. For the black hole, we have the following. First, in thermodynamics, the heat capacity is usually defined as the derivative of energy with respect to temperature, while keeping fixed other variables, perhaps if there are others, but if energy and temperature are the only variables, the heat capacity is just the derivative. And for the black hole, the energy is, we're taking to be the mass, so the heat capacity is dm dt. But T was 1 over 8 pi gm. So that means that m is 1 over 8 pi gt. And therefore, the heat capacity is minus 1 over 8 pi gt squared. It's negative. And it's negative because if you increase the temperature, the black hole mass is getting smaller. A big black hole is very cold with a very low temperature. But in general, thermodynamics with negative heat capacity is unstable. And you can see that here for the following way. Suppose we do have this black hole in equilibrium with radiation. That means it's emitting as much as it absorbs. But suppose by thermal fluctuation it emits a little bit more than it's absorbing. It loses mass, so its temperature goes up because the heat capacity was negative. And now it's hotter than its surroundings, so now it will emit more than its surroundings. It gets hotter still, and there's a runaway, and it will collapse to zero mass. Conversely, if it, by fluctuation, would absorb more than it emits, it would become colder, and then that would reduce how much it emits, so then it would continue to absorb more than it emits, and it would grow without limit. So the negative heat capacity makes the equilibrium unstable. Now, so that's the instability involving the black hole, but there's also instability involving the radiation. Suppose you've got a ball of black body radiation, let's say of radius r, temperature T, then the energy of that ball is of order, the volume is r cubed, but the energy density in black body radiation is T to the fourth. So the energy in that ball is r cubed T to the fourth, but then if you want to know whether it will collapse into a black hole, you have to look at this ratio, GE over RC squared, where we usually set C to 1, which therefore is G times r squared T to the fourth. So we find that a ball of black body radiation will collapse to a black hole unless this number is less than 1, which means unless r is less than roughly 1 over the square root of g times t squared. So a sufficiently big ball of black body radiation will collapse to a black hole, and therefore you can't, even before you introduce the black hole, you can't have, in a gravitating system, in the presence of gravity, you can't have a ball of radiation filling all, you can't have thermal radiation filling all space. So we can't have, with zero cosmological constant, perfect equilibrium between a black hole and radiation because they're, roughly speaking, both the black hole and the radiation are unstable. So therefore, you could ask what the discussion made. Well, we got a sensible answer for the assumed equilibrium, which agreed with what we calculated by a more detailed argument. But why, in fact, did that work? Well, the point is that although you see, our calculation was good, in the limit that g is going to 0, and as g goes to 0, both instabilities are turned off. So you can't have perfect equilibrium of a black hole with thermal radiation in an asymptotically flat space, but you can come very, very close to that as G goes as small, arbitrarily close in the limit that G goes to 0. So to see this carefully, we should discuss what we're keeping fixed in the limit as G goes to 0. First of all our discussion is about the limit as G goes to 0 because we didn't include loops of gravitons. So since we didn't include loops of gravitons, well, we ignored them, so our discussion was valid in the limit as G goes to 0. But we worked in a fixed space-time as G goes to 0. As we take G to 0, we can't take G to 0 with the black hole mass and the Schwarzschild radius both fixed. So the Schwarzschild radius is 2gm. So as G goes to 0, we can't fix both the mass and the radius. In our derivation, we worked in a fixed space-time. So we kept the radius fixed as G went to 0. So it's more natural for our discussion to think of the limit as G goes to 0 with fixed Schwarzschild radius, and therefore m is equal to Rs over 2G. So m is of order 1 over G as G goes to 0. And if we bear this in mind, then we can see that both instabilities are turned off. So what did I write here? Well, so for example, for the instability involving the black body radiation, we found that the maximum radius of black body radiation that doesn't collapse was that R was less than, at temperature T Hawking. We find that that was bounded by, 1 over the square root of G times Rs squared. I wrote it differently before when we derived it, but I think I wrote it as 1 over the square root of G times T squared. But now we want to evaluate this for T equals T Hawking, which is 1 over Rs. So therefore, the upper bound at that temperature on how big a ball of black body radiation can be is 1 over root G times Rs squared. And so, for example, so as G goes to 0, that's extremely big compared to the size of the black hole. And for example, if the mass of the black hole is the mass of the sun, then R is less than 10 to the 38 times the Schwarzschild radius of the black hole, which is much bigger than the size of the observed universe. So you can't have perfect equilibrium with black hole radiation going off to infinity in Minkowski space, but you can come very, very close to that. There's a similar story for the other instability involving the black hole. So the mass of the black hole was of order 1 over G, and then its temperature was of order 1 over Rs. So if there's a fluctuation and the black hole emits or absorbs a few too many quanta, its temperature will indeed increase or decrease relative to the surrounding radiation, but the change in its temperature, the change in the temperature of the black hole by absorbing a few quanta will be of order G. And that will indeed cause an instability, but since the mass was of order 1 over G, a change in the temperature by an amount of order G will only change the black hole mass significantly on a time of order 1 over G squared. And again, a time of order 1 over g squared for an astrophysical black hole will turn out to be a ridiculously long time. So, although thermal equilibrium between the black hole and radiation isn't perfect in an asymptotically flat spacetime, it's extremely good as g goes to 0. The instabilities are turned off as g goes to 0. That's why our discussion made sense. And that's why the heuristic argument based on equilibrium gave the correct prediction for what was going to be the effect of the potential barrier. Now, there's another answer in principle, which actually we will come to eventually. I'm not sure if we will do so tomorrow or Friday, which is that if the cosmological constant is negative, that turns off the instability involving the radiation, the one that I called B, and also the one from the black hole if m is sufficiently big. So we'll discuss that eventually. So with lambda negative, it actually is possible to have perfect equilibrium between a black hole and radiation. There are a couple of drawbacks. One is that in that regime, there's actually mostly black hole and not very much radiation. So it doesn't match very well your intuition about instability between a black hole and radiation. But also technically, when lambda is less than 0, the rest of our derivation doesn't work. Because, as we'll discuss later, when lambda is negative, outgoing radiation is reflected back from infinity. So we don't have Hawking emission in the usual sense. So for the derivation we've been giving of the Hawking effect and understanding the role of the potential barrier and its relation to equilibrium, I think the discussion with 0 cosmological constant was the natural one. But eventually we will get to the story for negative cosmological constant, where equilibrium can be completely stable. And that has other advantages because you can make more precise theoretical arguments. So any questions on any of that? Okay, now we really are finished section 4 in my lecture notes. So we're going to go on to section 5, which is on Rindler space and the Unruh effect. So what we're going to do is to explain a much more elementary situation, whereas originally shown by Unruh in not too long after Hawking's work, there's a much simpler situation in which you can see the origin of thermal physics. And today there will be an analogy with the black hole, but we'll understand more deeply later on why there is such an analogy. So there mainly are 2 papers here. I don't remember the exact dates, but roughly 1976 by Unruh and 1986 by Unruh and Weiss. So the essence of the Hawking effect was that the outside observer, by waiting, can see what's outside the horizon in the past with arbitrary precision, because you can see arbitrarily close to the horizon by just waiting, but you can see absolutely nothing about what's beyond the horizon. So the Hawking effect, if space is divided in an inside where you have no knowledge and an outside where you have perfect knowledge, somehow that leads to thermal physics. What we're going to do now is to investigate that situation in a simpler context, which involves Rindler space and the Unruh effect. So Rindler space is just the following. We take Minkowski space, but we take one of the coordinates that I'll call x, and I might abbreviate the others as y vector together. I also will sometimes write x vector for all the spatial coordinates. But it's one spatial coordinate that will play an important role. And now, by Rindler space on the right, we just mean the region where x is bigger than the absolute value of t. So it's bounded by past and future null planes. And so t goes this way, x goes this way. I'm ignoring y and z. This isn't exactly a Penrose diagram, but it will play the same role as a Penrose diagram. Usually in Penrose diagrams, we have spherical symmetry, and the spatial direction we plot is the radial direction. Here, we're only plotting one spatial direction, but it's x. We're not assuming rotation symmetry. Instead, we have translation symmetry in the y and z directions, and we're suppressing them. And similarly, there's a left Rindler region where x is less than minus the absolute value of t. And there are future and past regions up here and down here that won't play much of a role. We're going to be discussing the physics from the point of view of somebody who lives in one of these Rindler wedges, as they're called. Although this is the space-time picture, we're going to start with the Hamiltonian picture. So in the Hamiltonian picture, if you're interested in the right Rindler wedge, you'd say that you could pick an initial value surface, which is time 0, and whatever there's going to be in the right Rindler wedge could be considered to have originated from the initial value surface time 0. Similarly, that was the positive x part of the surface time 0. If you're interested in the left Rindler wedge, you would take the negative part of the surface time 0. So since Rindler wedge physics can be considered by causality to start from the physics on the initial value surface, in a Hamiltonian approach, you can deal with operators and wave functions on this hypersurface. And we're going to start with that point of view. So in Hamiltonian point of view, we just start with t and x, but we have this initial value surface, t is 0, but we divide it into the regions where x is positive and where x is negative. And we're going to look at the vacuum from the perspective of an observer who's only making measurements at positive x. So if you like, we're going to carry out the procedure that I described yesterday, which, as I mentioned, was first suggested by Sorkin, where we take the vacuum state in all of space-time, but we construct then a reduced density matrix for observations only in one region, which here will be positive x. Sorkin tried to consider a general region. So before we construct the reduced density matrix of the vacuum, we should first discuss how to describe the vacuum state. So how do you describe the vacuum state conveniently in quantum field theory in general, let's say by path integrals? Well, a well-known fact is that a path, first of all, we go to Euclidean space, so TE will be Euclidean time. So TE is, I guess, I times T to make this relation true. And then a convenient way to construct the vacuum state is to do a path integral on the Euclidean half space. So TE being 0 is T being 0 is the same as TE being 0, since they differ by a factor of I. And instead of thinking of the hypersurface on which you want to construct the vacuum state as living in Minkowski space at t equals 0, we think of it as living in Euclidean space at TE equals 0. And then we know that we can construct the vacuum state by a path integral on the negative half plane, TE negative. So starting with anything and then propagating through a semi-infinite amount of Euclidean time, we project onto the vacuum state. So this gives us a construction of the vacuum state. We think of the vacuum state as coming from a path integral on the negative half of Euclidean space. Now we'd like to construct the vacuum state as a pure state, but we can construct the projection operator onto the vacuum, which we can also think of as the density matrix of the pure state of the vacuum. So how would we construct the projection operator onto the vacuum? Well, that's just the product of the bra and the ket. So just as we constructed what I guess would be called the bra by a path integral of the negative half space, similarly we can construct the ket by a path integral in the positive half space. So a path integral on TE positive will construct the ket vector of the vacuum, and then a path integral on the region where TE is negative will construct the bra. And the product of the two gives the pure state, the projection onto the vacuum, or if you like, the pure state density matrix of the vacuum state. Now, in drawing the picture, just so we could see it, I've separated the two copies of the TE equals 0 axis. So both of these black lines represent TE equals 0. I've just drawn it twice so that you can see it. We have a copy of the negative half space that constructs the ket and a copy of the positive half space that constructs the bra, or else the other way around. It's always hard to remember which is which. But I mean it the way it's drawn on the picture. Now, in more detail, the vacuum state is a functional of some quantum fields. For simplicity, well, I'll just write phi for a generic quantum field. So the vacuum state we think of as a function of phi. Well, it's a function of phi on the initial value surface. So when we construct the vacuum state, as I said, we do the path integral on the lower half space, but we keep phi fixed. So we integrate on the lower half space, TE negative, over, well, I'll call it capital phi. Capital phi will be a field on all of space-time. Little phi will be a field at t equals 0. So we integrate over all fields with the condition that at t equals 0, phi reduces to the phi we want, times e to the minus action. Integrating over all fields on the lower half plane with the boundary values fixed at phi gives us the vacuum wave function as a function of phi. I hope that's a familiar construction in quantum field theory, since it's often used in different guises. We regard the vacuum wave functional as a function of the field on the time zero plane. And then we do a path integral on all fields on the lower half plane, keeping fixed the boundary values on the boundary. And that gives us a functional of the boundary values, which is the quantum wave function of the vacuum. So now, if we wanted to construct this density matrix of the vacuum, well, in more detail then, it's a function of two field variables, one above and one below the cut. So we now have the whole plane cut at TE equals 0, and to make it visible, I'm separating the two copies. And the only tricky part is to remember what we want to call phi and what we want to call phi prime and not make too many mistakes. So I call this one phi and this one phi prime, I hope. So then the vacuum state density matrix is a functional of phi and phi prime. And we compute it by doing a path integral on the lower half plane with the boundary value specified to be phi on the upper boundary of the lower half plane, and then the boundary value is phi prime on the lower boundary of the upper half plane. Now, okay, that gives us the pure state density matrix of the vacuum for observations on all of space. Now what we're going to do next is to integrate out the values of the field to the left of x equals 0 and get a density matrix good for observations to the right of x equals 0. Now I should warn you that when we do this, we're entering a world where things are not completely mathematically rigorous, because this separation introduces the ultraviolet divergences that Sorkin encountered when he tried to calculate the entanglement entropy, and we'll see some examples later on, though I better not promise how many because I'm not sure how far we'll get. So we'll use it, but anyway, the formalism of density matrices we're using is not quite applicable rigorously in quantum field theory. Of course, it would be applicable in a cutoff version of quantum field theory, for example, with a lattice cutoff, but the lattice cutoff would spoil Lorentz invariance, which will be important in a little bit. So a lattice cutoff cannot be used to make the argument I'm going to give today rigorous. There actually is a rigorous version using Tomita-Tokosaki theory, as first interpreted in this context by Sewell in 1982. This is about 6 years or more, maybe, after Unruh's first paper. I actually have a clean conscience in cheating in the following sense. I wrote a previous set of lecture notes explaining the use of Tomita-Tokosaki theory and the rigorous version in this context for physicists. So I can conscientiously refer you to that if you want to know what the rigorous version is. And today, we're going to simply use the informal version. Not only today, but in the lecture notes I have put on the web that are related to these lectures a few weeks ago, we have only the rigorous version of all these arguments. So I've made my apology once for these lectures. I'm not going to keep repeating it. So there will be numerous times when I'll say things that could be done more rigorously with Tomita and Tokosaki theory, making the arguments longer. And instead, we'll be giving not completely rigorous shortcuts with density matrices. And I won't repeat the apology. In the written lecture notes I did, you'll find a few footnotes where the apology is repeated every time it comes up. But in the lectures, I won't repeat the apology. So anyway, what we want to do, we have a representation of this pure state density matrix for the vacuum for observations in all space. And now we want to look at it for the perspective of an observer who's only measuring at x positive. So for that, first of all, we think of the field phi as being a pair, phi left and phi right, where phi left lives at x negative, phi left lives at x negative, phi right lives at x positive. And of course, they share a common value at x equals 0, which we're going to ignore. That's part of the slightly non-rigorous nature of this type of presentation. And so we'll think of the big Hilbert space, which consists, a generic element of this Hilbert space is the space of functions of phi. We'll think of a function of phi as a function of the pair phi left and phi right, where we'll think of the Hilbert space as being a tensor product h left tensor h right, where an element of h left would be a function of phi left and an element of h right would be a function of phi right. So this decomposition would be completely rigorous in a lattice theory as long as there's no lattice point at x equals 0, right? If we have, let's say, if x equals 0 is midway between two lattice points, so if lattice points are at 1/2 epsilon, 3/2 epsilon, 5/2 epsilon on one side, -1/2 epsilon, -3/2 epsilon, -5/2 epsilon on the other side, then this tensor product decomposition would be correct, and phi left and phi right would not share a point in common. The only, as I said, the only reason that that isn't the basis for a rigorous version of today's argument is that it would spoil Lorentz invariance, which we will want to use. Later on, we'll do some calculations involving this splitting where Lorentz invariance won't be important. So for those calculations, the lattice cutoff, when available, actually is a basis for a rigorous treatment. Okay, so anyway, our point of view now is that the vacuum state is a function of phi left and phi right, and it lives in this Hilbert space HL tensor HR. And we want to construct the density matrix for observations only in HR, only by operators that act on HR. So the density matrix rho R is supposed to be the trace over HL of this pure state density matrix where, in more detail, omega in the ket is a function of phi L and phi right, and omega in the bra is a function of phi L prime and phi right prime. And then we're supposed to take the trace over H left to get a density matrix for observations in the right half of space only. Well, how do we take the trace over H left? What it means to take the trace over H left is that we sum over unobserved states or unobserved variables. We sum over the values of unobserved variables. Well, what will be unobserved is phi left. So we sum, which will mean integrating over the value of phi left. But taking the trace means that you set it equal in the bra and the ket, and then you sum or integrate over it. So the density matrix we want will be a function of phi right and phi right prime that we get by integrating over phi left in this pure state density matrix. So I take what I had before, but I said phi left equals phi left prime. And then I integrate out phi left. So after doing that, we get something that depends only on phi right and phi right prime, which is appropriate for a density matrix for an observer only on the right-hand side. Saying it's a matrix means it depends on an initial and final state. And the initial state is described by phi right prime, and the final state is described by phi right. But in path integrals, so now what we do, so we have phi right and phi right prime that we leave alone, but we want to set phi left equal to phi left prime and integrate over them. What it means to set them equal and integrate it in path integrals is we set this value equal to this value. So I erase that part of the cut. That part of the cut is no longer necessary. I just glue the two together. And previously we were integrating over all values in the lower half plane and all values in the upper half plane, keeping fixed the boundary values, but now we want to integrate over phi left after setting phi left equals phi left prime. That simply means we want to integrate over everything except phi right and phi right prime. So we get a picture I can draw like this. There's now a cut only for positive x. And we integrate, this is at x equals 0. This is, t is in this direction, so the cut is at t equals 0, or te equals 0. So we integrate, we do a path integral in the whole cut plane with a cut along the x positive part of time 0. So if we were in 2 dimensions, we would just have a cut along this ray, and we integrate do a path integral on the rest of the plane. We're not just in 2 dimensions, there are more dimensions that are suppressed in this picture. So the cut is along this ray times the transverse directions, which if in 4-dimensional space-time would be 2 suppressed transverse directions. So the cut is on half of the time 0 surface. So a path integral on Euclidean space with that cut on half the initial value surface computes the density matrix of the vacuum state for observations in the right half space. Okay, well, what is this? We'll give a more practical way to compute that density matrix in a little bit. But to motivate it, let's go back to a space-time picture and discuss what this density matrix is supposed to be good for. So here I'm drawing the null lines x equals t and x equals minus t. They're the boundaries of the right Lindner wedge and the left Lindner wedge. And they're invariant under boosts of the xt plane. They preserve the two Rindler wedges. And as we'll see, boosts of the Rindler space are very important symmetry. There also are translations in the orthogonal directions that are suppressed in the picture, and rotations in those directions. They're there and they're important, but the really important symmetry of the picture are the boosts of the xt plane. That symmetry was completely lost in our discussion so far in the Hamiltonian picture. So we constructed the density matrix in a way that, first of all, explained why it is the density matrix of the vacuum for observations in the right half of time zero, but completely suppressed the space-time picture in Lorentz signature. So, but you see, as I actually did say before, the density matrix on that half space is, by relativistic causality, is supposed to completely control measurements throughout the Rindler wedge. And the Rindler wedge, of course, has Lorentz invariance, which we're now going to incorporate to reinterpret the density matrix that we found. Before I do that, though, we could discuss how Lorentz invariance acts on the Rindler wedge. So, sorry. Well, I didn't plan this very well, I'm afraid, but if you take a Lorentz boost of the Rindler wedge, it acts by moving you forward. If you normalize it so it maps you forwards in time in the right Rindler wedge, it will map you backwards in time in the left Rindler wedge. And then it will act like so in the what you could call the past and future wedges. So if you're living in the right Rindler wedge, you have a future horizon. You can't see past the line x equals t, as long as you stay in the right Rindler wedge. And you also have a past horizon. You can't influence anything past the line x equals minus t, the surface equals minus t. Yeah, I should have better explained that. The reason for the analogy between, the analogy between Rindler space and the black hole involves several ingredients that we'll gradually understand. But one elementary one is that if you stay in the Rindler wedge, the right Rindler wedge, for example, what you can see is bounded by a future horizon, just as if you're interacting with a black hole. And it's also bounded, what you can influence is bounded by a past horizon. So this is an example of an observer who's bounded, what that observer can see is bounded by horizons. Now, a difference from the black hole is that to stay forever in the Rindler wedge, you'll have to accelerate indefinitely in the future. If you ever stop accelerating and go in a straight line, a time-like straight line, you'll leave the right Rindler wedge after a while. So to stay in the right Rindler wedge, you have to keep accelerating into the future. And if you wanted to always be in the right Rindler wedge in the past, you must have been also accelerating in the past. So in a bit, we'll discuss the perspective of an observer who always accelerated and was always in the right Rindler wedge. But for now, I just observe that a difference from the black hole is that staying in the right Rindler wedge requires this constant acceleration. Whereas in the case of the black hole, you could be traveling on a geodesic that orbits the black hole at a big distance. You're not accelerating, you're just on a geodesic. And you stay forever outside the black hole. Whereas to stay forever in the right Rindler wedge requires acceleration in the past and future. But on the other hand, we'll also see a lot of similarities. So what we want to do is to reinterpret this density matrix we found from the point of view of the Lorentz symmetry of the right Rindler wedge. But since we constructed the density matrix in a Hamiltonian framework, to do that we want to look at the Lorentz generator in a Hamiltonian framework. So the boost generator, which I'll call K, can be written as an integral in Lorentz signature, an integral over time 0, an integral over all the spatial coordinates of x times t0, 0, of x spatial coordinates at time 0. That's a standard formula for the Lorentz boost generator as an integral at time 0. And by the way, okay, you see locally it looks like the Hamiltonian, but it looks like the Hamiltonian times x. So if you're located at a given value of x, for observations at x near a constant, x0 equals constant, k is approximately x0 times the Hamiltonian. So you can see that if x0 is positive, you have k is a positive multiple of the Hamiltonian. If it's negative, you have a negative multiple. That's the reason, or a way to see this picture, where k moves you forward in time on one side, backwards in time on the other side. That sign difference is very important. So this is the boost generator as an operator on the complete Hilbert space. But we want to take this useful but non-rigorous point of view involving factorization of the Hilbert space as a tensor product of h left and h right. So we want to write, is there a question? Okay. Apparently causing a lot of pain if there's no question. We want to write the boost generator as a sum or difference of operators that act separately on h left and h right. To do that, I'll define k right to be the part of this integral at positive x and then I'll define k left to be the part of the integral at negative x, but since x is negative, I'll put in an absolute value, so I still get an operator that would move us forward in time. And because I've done that, the relation between k and kr and k left is that k is k right minus k left. And k right formally is an operator on h right. K left is an operator on h left. So now we go back to our density matrix. Now we go back to Euclidean signature. So K becomes I times a rotation generator in Euclidean signature. So now so K was a boost of x and t. But instead, IK we can think of as a rotation generator of the Euclidean space, TE and X. So now we want to consider from this point of view the density matrix for observations in the right Rindler wedge. Actually, I'd like to draw it in a way that is more compatible with rotation symmetry. So I don't really know how to draw it, but try to imagine the region I'm shading is round. I'm drawing a big disk. This big disk has got a cut on the positive x-axis. So we have a big disk centered at the origin. And starting at the origin and going off to the right, we have a ray, and we cut the disk along that ray. And now you can see we could build up the disk by starting with this ray and rotating it through an angle 2 pi. So suppose we wanted to rotate it through a general angle. If we rotate it through a general angle, we'd have this kind of region. a wedge, let's say, of opening angle theta. And then we could specify a value, well, I hope I'm being consistent, but I hope I'm being consistent about where I put the primes. I could specify initial and final values phi right and phi right prime for the field on the boundary, and then I could do a path integral on that wedge. So that's a description by a path integral, but you can think of it as a description of an operator. The input to the operator would be a function of phi right prime, and you do the path integral on the wedge. Well, you'd compute the operator will be e to the minus theta times k right. So we start with the state psi of phi right prime, and we want to construct a new state, e to the minus theta k right on psi, and it'll be a function of phi right. And it's given by an integral over the field phi on the wedge with the boundary values that phi is phi right on the upper boundary and phi right prime on the lower boundary, as shown, e to the minus the action, except then you have to multiply by the initial state, psi of phi right prime. I have no idea whether the kind of manipulation I'm making is so familiar that a sketchy description is sufficient, or if, on the other hand, I'm baffling half the audience, I'm afraid. So, in general, an operator you can represent by a kernel that's a function of initial and final variables. And the kernel would just be gotten by the path integral on the wedge with initial and final values phi right prime and phi right. If you want to write it explicitly as an operator, you have some initial state psi, and you integrate the kernel times the initial state over the initial variable phi right prime to get explicitly the output state as a function of phi right. One way or another, I hope you can imagine the path integral on this wedge as a path integral construction of an operator e to the minus theta k right. Well, now what we're going to do is to just consider a couple of special values of theta that are important. First, we'll set theta equals 2 pi. And what is a wedge of opening angle 2 pi? Well, it means we rotate all the way around and come back to the starting point. And that's the path integral that constructed our density matrix. So we learned that the density matrix rho right is the special case theta equals 2 pi of what we get from the wedge. So it's e to the minus 2 pi times k right. Similarly, if we'd studied it on the left, we'd have learned that rho left is e to the minus 2 pi k left. Now, a question you might ask me was whether this density matrix is correctly normalized. So how do we compute the trace of rho right? Well, to compute the trace of rho right, what it means to compute the trace, in general, to compute the trace of an operator, you sum over all its diagonal matrix elements. You get a diagonal matrix element by setting the initial and final states to be equal, which here means we set the values below and above the cut to be equal. And then we sum, or in this case, integrate over those values. So in other words, to compute the trace, we glue together the fields along the cut. And now we're just integrating over all space. So the trace is just the path integral in the whole of Euclidean space. So it's formally equal to e to the minus the volume of Euclidean space times the ground state energy. So assuming we normalize the theory so that the ground state energy is 0, assuming we renormalize, our renormalization was chosen so the ground state energy is 0, the global path integral is 1, and our density matrix is correctly normalized. If we didn't do that at this point, we'd have to divide by a normalization constant to get the density matrix. Okay, are there any questions on what I've said so far? So we've arrived in, this is an extremely important result. Well, this or its rigorous version in Tomita-Takasaki theory are extremely rigorous, extremely important statements. Sorry, did I say it was extremely rigorous? I meant to say it was extremely important. I don't remember what I did say. So, heuristic interpretation. Yes?
Questions, just a second. There are two questions I saw.
In the definition of K, why we took it with a minus sign, KR minus KL?
Well, I define KL with a minus sign. You can ask why I did that. Yeah. I could have just put X here, but then it would be negative. I wanted to define KR and KL so they both would move you forwards in time. So I defined KR and KL in a reflection symmetric way that treated positive and negative X equally. But K is odd under reflections. So if I'm going to define KR and KL in a reflection symmetric way, there has to be a minus sign in the formula for K. The picture is asymmetrical here between left and right. The boost that maps you forward in time if you're at positive X maps you backwards in time if you're at negative X. So somewhere there's a minus sign. If I didn't want a minus sign here, I should remove the absolute value here. And then this operator would map you backwards in time because X is negative. Any other questions? Yes? I think the question is, why does the path integral in a wedge compute the action of e to the minus theta kr? Is that the question? Well, let's start with the more elementary question. Suppose we were trying to compute e to the minus theta times h. What kind of path integral would compute that? We'd have a slab of thickness theta in Euclidean time, and the path integral in the slab would construct e to the minus theta h. Why is that true? It's because h is the generator of time translations. So geometrically, if you generate time translations by an amount theta, you construct the slab, and therefore the path integral in the slab computes the matrix element of e to the minus theta h. Now, if instead we take e to the minus theta kr, acting just on the half line or half initial value surface, it's generating a rotation. So the geometrical transformation it does is to generate this. And whatever derivation convinces you that this path integral computes that would hopefully convince you that this path integral computes that. Any other questions?
Maybe one more question. So boost is a conserved charge provided there is a local conservation law for the stress energy tensor, but now we put a boundary. So in the presence of boundary, in principle, we have to require a certain boundary condition on the stress energy tensor for this K right and K left to be conserved.
If you want to ask that kind of question, we should learn Tomita-Takasaki theory and discuss the rigorous version of this. It reaches the same conclusions that we're reaching more informally. And as I said before, I highly recommend my lecture notes, which were called Notes on Some Entanglement Properties of Quantum Field Theory. I think you'll find that to be the most I don't want to say the most, but a particularly elementary treatment of Tomita-Takasaki theory for physicists. And you can read about its application here or to the black hole. But in these lectures, we're going to skip Tomita-Takasaki theory and give informal explanations. The reason is not only that that's quicker and avoids learning Tomita-Takasaki theory, but unfortunately in this subject, it's impossible to be completely rigorous. So now I'm telling you something that does have a rigorous version in Tomita-Takasaki theory. But eventually we're going to be discussing things that don't have known rigorous versions. So we have to get used to the non-rigorous informal arguments. Any other questions? Yes?
I'm sorry, I'm not sure if I understood, but my question was about if there has to be done some considerations about the boundary effects of the cutoff. I don't know if it was
Your question is about the boundary conditions at x equals 0?
from the cutoff. Also, does it has any relevance to do?
Well, the role of the cutoff is that it spoils Lorentz invariance and keeps us from making this argument. So that's why I do not have a rigorous version of this argument based on a cutoff version of the theory. The only rigorous version that's known of this argument I'm telling you is in Tomita-Takasaki theory, which we don't want to, if you want to have, well, it should have been a different set of lectures, which I actually have given in past years. I just wasn't going to do it here, where we do Tomita-Takasaki theory and give rigorous versions of some of these things. So all questions about boundary conditions, I will refer you to Tomita-Takasaki theory. We have to accept that what we are discussing now is non-rigorous, and although it could be made rigorous at the cost of a lot of technicality, we eventually will want to understand things that can't be made rigorous in any known fashion as of 2025.
I have a very quick
That's
question.
why I'm going to dismiss all questions on boundary conditions in the same way, no matter how many are asked. Any other questions?
So, just a small question that's related to it. So it's still a conjecture, right?
What is a conjecture?
Kawasaki theory.
No.
So it is.
Tomita-Takasaki theory was developed rigorously half a century ago. By coincidence, also in the same years that Bekenstein and Hawking were starting black hole thermodynamics. So Tomita-Takasaki theory is a rigorous mathematical theory in operator algebras. And it was applied to this problem that we're talking about by Sewell in 1982. So there is a completely rigorous version of what I'm telling you today, but not of everything I'll tell you in successive lectures. Well, any more questions, but preferably not questions that will get the same answer.
So I might be jumping ahead a little bit, but can you say in a couple of words the things that can't be done rigorously in Tomita-Takasaki?
Everything I'll say today has a rigorous version. But I can't tell you in a couple words everything I'll say today. We have to be patient.
But the things that are not rigorous in Tomita-Takasaki.
When I get to something, we won't get to anything non-rigorous today. When it happens, I'll let you know.
Wonderful.
Okay. Well, any more questions, preferably not about gaps in rigor? By definition, we wanted to integrate out phi L to construct a density matrix that depended on observations of phi right only. So we said phi L equals phi L prime and integrated. An excellent question in the spirit of today's lecture. Well, I'll go on if I'm not stopped by more questions. But I forget where we were. Okay. So we had concluded that the density matrix of the right Rindler wedge was e to the minus 2 pi kr. And heuristically, that means that physics in the right Rindler wedge is thermal. Well, it's thermal with Hamiltonian kr and inverse and temperature 1 over 2 pi. So this is a thermal density matrix if kr is understood as a Hamiltonian and 1 over 2 pi is the temperature. Now you could ask, well, since kr is a slightly weird Hamiltonian, what it looks like. And I think I already told you that for observations at, let's say, x approximately L for some constant L, K, R, is approximately L times the ordinary Hamiltonian. So such observations will see ordinary thermal physics at a temperature 1 over 2 pi L, right? The Hamiltonian is L times the ordinary Hamiltonian, so it's as if the temperature was 1 over 2 pi times L. To be a little bit more detailed about that, in case it was confusing, e to the minus 2 pi kr we approximate for observations near x equals L as e to the minus 2 pi L times h. And so you see that the effective beta at L is 1 over 2 pi L. So for observations at L, for observations near x equals L, you'll see approximately ordinary thermal physics, but at a temperature that's inversely proportional to L. So we can consider a simple example of making observations at a definite value of x. For that, we can consider a simple case that Unruh originally considered in the first of these two papers, of an observer who is going to remain forever in the Rindler wedge. He simply considered a uniformly accelerated observer. So any universally accelerated observer in Minkowski space by a Poincare transformation can be put in the form I'm about to write for some choice of the Rindler wedge. So in this presentation, we'd started with the Rindler wedge, and now I'm about to whip out of left field a uniformly accelerated observer. Instead, we could have started with a uniformly accelerated observer and then picked a corresponding Rindler wedge. So a nice example of an observer who stays forever inside this Rindler wedge is a uniformly accelerated observer where T is L times, I guess, cosh of tau over L. X is, sorry, this should have been sinh, I think. X is L times cosh of tau over L, and Y and Z are 0. I'll get to your question in a second. So that's an example, a simple example of an observer staying forever inside a Rindler wedge. It's a nice, to do that, you have to accelerate indefinitely in the past and future, and this is a simple example with constant acceleration. And now we notice something very nice, which is that this orbit is periodic in imaginary time. Periodic in imaginary proper time. So suppose that the observer measures, I'm going to let capital X be the set of all coordinates, Tx, Y, Z. The observer measures, what would an observer measure? Let's suppose for simplicity that an observer measures a quantum field along the observer's orbit. So the observer measures 5x in tau times 5x in tau prime along in the Minkowski space vacuum. But the observations are made along the orbit. So x of tau and x of tau prime are of this form with different values of tau and tau prime. Well, those observations are going to be periodic in imaginary time because the orbit itself is periodic in imaginary time. I'm cheating slightly. The rigorous statement is that this two-point function will satisfy the KMS condition. It's actually explained that way in the same lecture notes where I explained comedic Takasaki theory. But anyway, informally, since the orbit is periodic in imaginary time, the observer will see thermal correlation functions. And you see, the period is going to be the periodicity of the orbit itself. So the orbit is periodic with period tau going to tau plus 2 pi I over L. And that will correspond, 2 pi IL, not 2 pi I over L. So beta is 2 pi L. And the temperature for this observer who's accelerating in a way that determined by this L is 1 over 2 pi L. So that's what we expected intuitively because the Hamiltonian this uniformly accelerated observer is always at a proper distance L from the origin. So I explained that K looks like L times the ordinary Hamiltonian, but I explained it in a way that involved being at time 0. But actually, it's a Lorentz invariant statement. So K, if you're at a proper distance L from the origin, well, for this type of observer this uniformly accelerated observer has an orbit that's simply the trajectory of this observer is an orbit of the one parameter group generated by what we called K. So with K regarded as a time translation, this is a time translationally invariant orbit. So at any point along the orbit, K looks like L times the local Hamiltonian. And therefore, the heuristic argument would have suggested that the observer will see thermal physics at temperature 1 over 2 pi L, which is what we get because of the periodicity of the orbit, periodicity of the trajectory in imaginary time. And which we can also get more rigorously by, well, showing that the 2-point function measured along the orbit satisfies what's called the KMS condition. So are there more questions here? Yes?
You just answered my question, but I'll say it anyway for other people. I think you have a small typo on the slide before. You wrote beta equals 1 over 2 pi L, and I think it should just be 2 pi L. So people might want to correct that.
No, the period is tau going to tau plus 2 pi L.
If you go one slide up,
Oh,
a bit more, there's beta L, I think. Yeah.
yes, thank you. Any other questions?
Sorry, I might be slightly confused, but the Hamiltonian for the observer on his trajectory, is it h or is it LH, which is k? Because the translation along the trajectory, I would assume, is generated by k, right?
Well, I think K over L is the observer's Hamiltonian. Let's see. Well, if by the observer's Hamiltonian you mean that which acts as d by d tau,
Yes.
which is what the observer would want to call the Hamiltonian. So K acts by delta t equals x, delta x equals t. So I think there's an L between K and d by d tau. I'll make a mistake if I try to say which has an L relative to the other, but one of them does.
So the temperature the observer measures is 1 over 2 pi L.
That's what I said.
Okay. And,
I did say that.
But
Yeah,
I think if you take the Hamiltonian to be k, then it would be 1 over 2 pi.
Well, yes, I also said that. If you take it's true. If you take the Hamiltonian to be k, then you'd say the temperature is 1 over 2 pi, but the observer would more naturally take the Hamiltonian to be k over L, and then would say that the temperature has an L in it. I will keep making mistakes about whether L is in the numerator or denominator, so I want to finesse that. Any other questions? So, okay, I think I still have a few minutes to explain one more important fact about this setup. So first of all, in general, if rho is a density matrix on some Hilbert space H, a purification of rho is a pure state psi in H tensored with some other Hilbert space H prime, such that rho is the corresponding density matrix for observations only on H. This is probably a familiar notion. So in this case, rho equals e to the minus 2 pi kr was defined as the trace over h left of the vacuum projection operator. So by definition, the vacuum state is a purification of rho r or of rho l. However, it's a very special purification. So here, a given rho would have a lot of possible purifications. But here, the vacuum state is a very special purification. So there are two senses in which it's special. First of all, well, what is the vacuum state? Well, the vacuum state was a function of phi left and phi right that we computed by a path integral in the lower half plane. But you can see the lower half plane is a special case of a wedge. It's just a wedge. If you take a wedge with angle pi, you get the lower half plane. 2 pi gives you the whole plane with a cut on the positive axis, but pi gives you the lower half plane. So psi of phi left and phi right is associated with e to the minus pi times kr, while rho is associated with e to the minus 2 pi times kr. So e to the minus pi times kr is an operator. So if you want to write an integral kernel for the operator, that's a function of a pair of variables, the initial and final state, which here interpreted as phi left and phi right. Previously, we called the initial and final state phi right and phi right prime, but now we want to call them phi left and phi right. We take maybe phi left and we rotate through an angle pi, and at the other end we have phi right, and that path integral computes the integral kernel of the operator e to the minus pi k right as a function of phi left and phi right. However, this has this has another important interpretation, which is that what we're constructing is called the thermofield double. So we've discovered that Rindler space is a kind of thermal system. So let's discuss thermal systems in general. So if you have a Hamiltonian H, inverse temperature beta, on a Hilbert space curly H, and then you have a thermal density matrix 1 over Z times e to the minus beta H. Okay, that's a nice example of a density matrix, but that density matrix has a particularly nice purification, which is called the thermofield double. So the thermofield double is a purification of rho that's especially nice. It's in a Hilbert space that people usually describe as the tensor product of two copies of H. But more canonically, it's the tensor product of H with its complex conjugate, or time reversal conjugate. And the state, psi TFD, is it's 1 over the square root of Z times e to the minus beta over 2H. So as written, that's an operator on, as written, psi TFT is an operator from H to H. But by duality, an operator from H to H is the same as a vector in H tensor H prime, where if this was an abstract vector space, you'd say that H prime is the dual vector space. But for Hilbert spaces, it's natural to call it the complex conjugate. Now, as I said, in the majority of physics, informal physics discussions of the thermofield double, you'll find the difference between a Hilbert space and its complex conjugate ignored. That's natural if you have a time reversal invariant system with t squared equals 1. But anyway, it's what people usually do. So it's what you'll usually see. So, as I said, if we have a thermal density matrix, well, okay. If I take its square root as an operator, so the operator rho is 1 over z times e to the minus beta h. Its square root as a positive operator is 1 over the square root of z times e to the minus beta h. But we can regard that as a vector in H tensor H prime. And if we do, it's actually a purification of rho. People usually like to write this more explicitly. So rho would be 1 over z times the sum over states, e to the minus beta times ei times I, and psi TFD would be 1 over the square root of z times the sum over I of e to the minus beta ei over 2 times I prime, where I prime is the counterpart of I in what people usually call simply a second copy of H, although it's better, more canonically, it's the complex conjugate of H, as I keep telling you. If you take this formula for psi TFD, then following standard reasoning, you'll see that the corresponding density matrix is rho, so that psi is indeed a purification of rho. If we want to regard psi as an operator rather than a state, you just see. The definition of the complex conjugate of a vector space is just a cat in one space is a bra in the other space. So, as an operator, this is 1 over the square root of z times e to the times the sum of e to the minus beta ei over 2 times the projector onto I. And so it's rho to the 1/2. So the thermofield double state of a thermal density matrix is the square root of the density matrix regarded as a state rather than an operator. In fact, that's a canonical quantization. That's a canonical purification of any density matrix. To purify any density matrix, you can take its positive square root and regard that as a state rather than an operator, a state in a double Hilbert space. And that's the canonical purification of any density matrix. So what we've discovered here, so there are two important results today. One is that rho r is thermal. And the second is that the vacuum state is the thermofield double state. Of the pure state rho r. Of the density matrix rho r. So if you take the thermal density matrix rho r, the corresponding thermofield double is simply the vacuum state in Minkowski space. So these are the, these and various things we explained that are related to the first statement, I guess, are the important results about Rindler space and the Unruh effect. And with that, I think I'll leave you for today, modulo further questions.
Okay, thanks a lot. So I think we have time for a few more questions.
Hello. Thank you for the. Can you hear me? Yeah. Okay. Here, yes. Thank you for the nice lecture today. So a quick question about this. When you prepare the vacuum state with this angle theta equals to pi, the lower half space. So isn't that a rotation in the clockwise direction? So theta equal to negative pi maybe, or those subtleties, for example?
Well, when we're propagating through Euclidean time, we're always going to get damping operators. And since k right was defined to be positive, no matter what we do, we're always going to get the exponential of k right times something negative. So the type of question you're asking can be confusing, but we're always going to land on our feet, because in Euclidean space, path integrals will always suppress the state. So the question is, what's a purification? If rho is a density matrix on a Hilbert space H, well, usually the way we get density matrices is we start with pure states and then we construct associated density matrices. But if you've got a system in the lab, in general, it would be described by a density matrix, and well, you might not know with what other system it can be combined into a pure state. But mathematically, it's often convenient to study density matrices by choosing a purification. So a purification of rho, which might be simply a mathematical device, you might not, well, a purification of rho is a pure state psi in H tensor H prime for some Hilbert space H prime, such that rho is the corresponding density matrix on H. So to get the corresponding density matrix on H, we take the projector onto psi, and then we trace out H prime. So what it means is that psi is a pure state somewhere on H tensored with something, such that the corresponding density matrix on the original system is rho. If you have a system in the lab and you know how it was made, you might know what is H prime, such that rho is the pure state corresponding density matrix on a pure state. But if you don't know how it was made, or if the way it was made involves something that was thrown away and has become entangled with the rest of the universe, you might not have a convenient choice of H prime that has any physical meaning. But in general, well, it's an important property of quantum mechanics that every density matrix does have a purification. And I actually explained that in the lecture, because rho to the 1/2 can be viewed as the purification of any rho. Rho to the 1/2 is an operator on H, but you can equivalently regard it as a vector in H tensored some other H prime, which is canonically the complex conjugate of H. And viewed as a vector in H tensor H prime, rho to the 1/2 is always the purification of rho. So it's not a unique purification of rho, but it's frequently a convenient one. And in Rendler space, it's very convenient because rho to the 1/2 has a natural interpretation. Since rho was e to the minus 2 pi k, and the vacuum state is e to the minus pi k, the canonical purification of the Rendler space density matrix is simply the vacuum in Rendler space. And there really were two important results in the lecture. One is the thermal nature of the density matrix, and the second is the fact that the vacuum is its canonical purification. I spent more time on the first result than on the second, but they're both very important.
We have made mathematical derivation the whole day, but is there naive physical interpretation that where the temperature of the black hole come from, like in classical thermodynamics, that temperature is the average kinetic energy of the molecules.
We're not going to get a more intuitive interpretation of temperature than we've gotten today in this lecture. So this explanation for Rindler space is the simplest explanation there is of why making observations only in a limited region of space-time produces effects that are similar to thermal effects. So what I've just explained to you is the simplest known explanation of this phenomenon. So if you didn't regard it as a simple explanation, you're going to be out of luck. You can try to do better, but until you or somebody does better, you'll be out of luck. Yes, I see a question back there.
Maybe this is a naive question, but two observers that are being accelerated at the same sort of constant rate in the Rindler wedge will see the temperature depend on their position from the origin.
Mm-hmm.
So what does that say for homogeneity in the wedge?
Well, first of all, the Rindler wedge doesn't have any symmetry. The Rindler wedge doesn't have any. The question was, well, okay. Consider this accelerated observer and this one who accelerates more slowly because that second observer is farther from the origin. They will indeed experience different temperatures, and that should be no surprise because there's no Poincare transformation that maps one orbit to the other. They're inequivalent orbits with different proper accelerations, and observers in those two orbits will see different things. It's not unlike asking about comparing an observer always at rest to one who's always accelerating. One observer will see the vacuum, the other will see a kind of thermal physics. Any other questions? Yes, here. Shout.
No, please, just wait for the microphone. There's one question from Zoom that maybe I pass on while we're waiting. So the question was whether purification is unique.
No, purification is far from unique. Let me tell you to what extent it's unique. So if psi in H tensor H prime satisfies the definition of a then one tensor psi, one tensor u, for any u, use a unitary on H prime. And one is the identity on H. So one tensor u of psi equals psi tilde obeys the same. This is the extent to which purifications are not unique. Two purifications of the same density matrix on the same Hilbert space H tensor H prime differ by unitary transformations of H prime.
Please go ahead. Sorry.
So perhaps related to the earlier question asked here before, isn't a direct computation with, well, smeared out versions of Unruh detectors giving a bit more physical picture of why you have some kind of thermal behavior, or at least you have some kind of radiative behavior by an observer accelerating? Or would you say that's not a sufficiently
I don't know.
Acceptable calculation?
I'm not sure what exactly the question is. Unruh and others have discussed this Unruh effect further from different points of view. So there's certainly more one could say about it than I haven't said. I have derived what I think are the really important results about it.
Okay.
No more on Zoom, so then let's thank Edward again.